computer audio. Yeah. Yeah. Okay. Participant, yes, is good. We have participants. Is good. So, okay. Yeah. Join us is good. And I need this one. The tools. Good. Joining. More real time. Screen. Application. Landscape. Full screen. Okay. Well, share screen. Share. Hello. Today we have a lecture. In this lecture, we are going to talk about some numerical examples about the sampling. Are you with me?
Yes, doctor, yes.
Oh, okay. So let us start with the example number 1. Okay. Now we are going to talk about 3 or 4 examples, inshallah. In these examples, we are going to illustrate how we are going to apply the theorem of the sampling. First of all, we have a very simple example, and then we are going gradually to increase the complexity of the examples. Now, example number 1. Okay, example number 1, EX1. In this example, suppose that you are given an analog signal. Of course, when I'm going to upload the video of this lecture, again, a PDF file will be uploaded, which includes the examples in detail. Now, example number 1, we have an analog signal, x of t equals to 5 cosine 2 pi multiplied by 1000 t. Okay, this is the signal. Now we have a signal which is omega. Now omega equals to 2 pi 1000 t. Sorry, 2 pi 1000. Okay, now what will be f? As you know, f equals omega naught divided by 2 pi. So f naught, or the fundamental frequency, will be 2 pi 1000 divided by 2 pi, and it will be 1000 or 1 kilohertz. This is what? This is the basic frequency or the fundamental frequency of this signal. Please, you have to write down your names in the chat. Okay, I'm going to save the chat for the attendance, please. Well, now, according to the Nyquist criteria, in the previous week, we said that we have Nyquist rate Fs is equal to 2F maximum. Okay, 2F max. Now, what will be the F maximum in this example? What will be the F maximum? Do you hear me or not?
500.
100, yeah, 1000 hertz. Okay, 1000 or 1 kilohertz is the maximum frequency. Why? In this example, all we have is what? Single cosine. So we have a single function. So the maximum frequency will be the fundamental frequency of this cosine signal, which is 1000. Okay, now continuation with this example. Of course, in this example again, we have an information. They have sampled this signal. They have sampled this signal by sampling frequency is equal to 8 kilohertz. Please write down your names in the chat. I'm going to save this chat. Well, now they have sampled this signal by sampling frequency equals to 8 kilohertz. Okay, Fs is set to 8 kilohertz or 8000. Of course, according to the Nyquist rate, Fs will be 2000. Okay, Nyquist rate will be 2000, but practically we have what? We have sampled the signal by 8 kilo samples per second. Now, what are the requirements for this problem? First requirement needs sketch the spectrum of original signal. Okay, sketch spectrum for what? For x of t. I mean sketch x of f. Requirement number 2, sketch the spectrum for the sampled signal. Okay, sketch the spectrum for the sampled signal from 0 to 20 kilohertz. Okay, what do you mean by sample signal? I mean sketch the spectrum for what? X S of f in the range of what? 0 up to 20 kilohertz. That's it, no more, no less. Okay, so we are given a signal which is 5 cosine 2 pi 1000t. The signal is sampled by sampling frequency equals to 8 kilohertz. Well, and the requirement will be sketch the sample signal x, original signal, I mean x of f, and then you are going to sketch the sample signal xs of f. Now, let us go to the detail of this problem. Now, how we are going to sketch the double-sided spectrum, of course, for the cosine signal? Well, x of t is defined by x of t equals to cosine, 5 cosine, okay, 5 cosine 1000 2 pi t. I'm going to what? I'm going to apply the Euler identity. As you know, Euler identity will expand the cosine signal into 2 exponential components. One of them lies on the right, the other would lie where? On the left. Now, using Euler identity, it will be equals to 5 over 2 multiplied by exponential j 1000 2 pi t plus e to the minus j 1000 2 pi t. Okay, so we have 2 components. Now, how we are going to sketch this one is very easy and very simple job. we are going to sketch the double-sided spectrum for this signal. As you know, this will be the f-axis, and this one will be the magnitude of x of f. Okay, magnitude of x of f. Now, the frequencies will be what? Will be 1000. Okay, so this one will be 1 kilo, this one will be 2 kilo, 3 kilo, 4 kilo, and so on. So this one is 1 kilohertz, this one is 2, 3, minus 1, and minus 2. Of course, we are going to modify f. Look, f, sorry, f in kilohertz. Okay, now f becomes in kilohertz. Well, now we are going to what? We are going to plot the signal. Two components we have. One of them lies at 1, the other at -1. Okay, and their amplitude is 2.5. Okay, so this is the first one, and this one the second one, and the amplitude will be 5/2, which is 2.5 in amplitude. Is it clear for you? We have what? We have sketched the spectrum for the sampled, for the original signal. Okay, are you with me?
Yes,
Yeah.
yes, sir.
Huh?
Yes, Dr. Yeah.
It's okay.
Saiba.
Balibra.
Saiba بس دونيف تاخد كيف هنا؟
Chawa.
دونيف 2.5
2 point من قلت تبني خوب ده ديف Euler Identity نكتب تبين بيسم اقدر نكتب تبين بيسم درسته. Okay, Euler should be Euler Identity بيجي cosine theta equals ch 1/2 e to the j theta plus e to the minus j theta. صح كامبليتيود كوساين كان ده بينجا بينج تقسيم دو دبنا دو نيف.
تمام سيدي درسته.
درسته برا؟ درسته.
بس.
Okay, now we have what? We have plotted the spectrum of the original signal x of f, and you can, as you can see, we have two components at 1 and -1, and the amplitude of each component is 2.5 according to the what? According to the Euler identity. Well, of course. Now, what we have now, we are going to what? We are going to sketch or obey the second requirement. Look at the second requirement. Second requirement talks about what? About sketching the sample signal XS of f. Okay, write down your names really. I'm going to save the chat. Well, now the second requirement will be the spectrum of the sampled signal. Well, before drawing the spectrum of the sample signal, first of all, we have to what? We have to sketch the spectrum for the sampling function. Well, S of f. Look, it will be as follows. This will be capital S of f, and here f in kilohertz. Look, please. This will be 8, this will be 16, minus 8, minus 16. Of course, the next one will be at 24 and minus 24. These are the what? The components of the sampling function. Okay, S of f. Now, how we are going to determine XS of f? Of course, by performing the convolution between what? Between x of f and
S of f.
and S of f. Good. Okay. And S of f is good. Well, so two spectrums, I mean the spectrum for the x of f is ready, and the spectrum for for s of f again is ready. Now all we need is what? To perform the convolution between these two signals. Again, I forget again, we have another component here at origin, of course, at 0, another component. Well, by now we can what? We can perform the convolution between these two signals. Let me take a new page, better. Well, lines and the grids is good. Now, we have sketched the original signal. Again, I'm going to redraw the sketch of the original signal. Two components we have at 1 kilo and at -1 kilo. 1 minus 1. Its amplitude is 2.5. This one is f in kilohertz. Now, the spectrum for the function s of f, spectrum for the function s of f. Let me show you s of f. Yes, this will be the s of f. Yeah. Well, now we have to use our scale. Okay, due to scale, I'm going to sketch capital S of f, f again in kilohertz. Okay, f, s of f. Of course, when I'm talking about the frequency domain, I'm using what? Capital letters. Look, x capital of f, s capital of f, and so on. Okay, now let us tick the x-axis for the sampling function s of f. Of course, say this will be the 8, 0, and 16. Okay, -1 and -8 and -16, 1, 8, and 16. This will be the 0. Of course, now look, why I am going to plot or sketch the S of f up to 16. Why? The requirement of the problem talking about draw the spectrum from 0 to 20 kilohertz, no more. Okay, so all we need is what? 0, 8, and 16. These are the sampling frequency. In the previous lecture, when we derived the formula, we said that the f-axis for the S of f will be what? Will be 0, fs, 2 fs, 3 fs, 4 fs, and so on. So here in this example, we have 0, fs, which is 8 kilo, 2 fs, 16 kilo. If you are going to talk about 3 fs at that time, it will be 24 kilo, and so on. No more, no less. Now, what will be the next step? The next step will be what? Will be the convolution between x of f and s of f. Now,
teacher, sorry for interrupting, but
yeah,
a simple question.
yeah.
We have fs 2 kilohertz, 2 hertz, 2 kilohertz, sorry, and you use 8. Why?
We have two
2
what?
kilohertz.
Yes, yes.
When
Okay.
according to Nyquist, right?
Well, good. I said when we start the example, I said what will be the Nyquist rate? Nyquist rate is 2 kilohertz. Okay, but
Yes.
in the problem requirement, due to the problem requirement, the sampling frequency is fixed at what? At 8 kilohertz.
So it depends on the requirement.
Yeah, on the requirement. Yes. Okay, in the requirement.
Okay, got it.
But at the beginning, I have told you how we are going to determine the sampling rate. Okay. So in this example, it's a good question for. Thank you for the question. In this example, we have selected the sampling frequency greater than what? Greater than Nyquist rate. Okay, greater than Nyquist rate. So in this way, we can guarantee that there is no overlapping. Okay. In this example, in this example, sampling frequency is greater than Nyquist rate. Okay, 8 is greater than 2. Okay, so in this way we can guarantee that there is no overlapping. Okay, so no overlapping, or say aliasing. We don't have aliasing or overlapping. It's good. So by now we have what we have. Just give me one moment. Yes.
Excuse me, sir.
Yeah.
So as we know, it should be the frequency equal or greater than Nyquist rate to we can
Avoid overlapping. Yes.
yes, for
Yeah.
avoiding overlap and recovering our signal. Yeah.
Yeah. It's
So
good.
what will happen if it be a 1.5 kilohertz?
Yes. Do you know? I have 3 examples really in this lecture. Now, the first example is the easiest one. Okay. Now, in the next example, I'm going to take the critical sampling rate. Then we are going to take less than Nyquist rate. What will happen? Okay. Of course, overlapping will occur, but I'm going to show you numerically what's going on. Okay. In example number 3, inshallah, it will addresses the problem of overlapping. Okay.
Okay. Thank you.
Good. Now let us continue with the example number 1 and perform the convolution between these 2 signals. As we have told you before, we said that to perform the convolution between delta function and any function, for example, say delta of f, generally delta of f minus fs convolve with x of f, the answer will be what? X of f minus fs. Okay, this is what is a formula. Okay, we have to keep in our mind this formula in order to what? In order to perform the convolution. Well, now we have the 2 graphs. So first of all, I mean the first component will be what? Will be x of f convolve with what? With delta of f. Convolve with delta of f. Of course, the result will be what? Will be x of f itself. Well, x of f. Now, second thing, we have what? We have this component. Of course, this component will be what? I mean, second one, we have what? X of f convolve with what? Delta of f minus what? Minus 8. And in this time, the result will be what? Will be x of f minus 8. Okay? Third one will be what? X of f convolve with delta of f minus 16. And the result will be x of f minus what? Minus 16. Is it okay? Of course, we have the effect of the negative components again. Well, so we are going to perform the convolution between x of f and delta of f plus 8 and delta of f plus 16. Okay, again we have what? It will be x of f plus 16 yes, and x of f plus 8. This is about what? About the convolution between these 2 signals. Okay, by now I have illustrated the operation. Now, is it a difficult job? No, it's a very simple job. Just I'm going to what? Just I'm going to shift the center of x of f. At the beginning, it will appear at 0. Second time, it will appear at 8. Third, at 16. Then at minus 8. Then at 16. Now, let us draw this signal. this will be the axis, frequency axis, f in kilohertz. Of course, we have to put ticks for the 8 kilohertz. Okay, say this is a 0, this one 8, for example, 16, or let me use 4 ticks for every yes, 1 2 3 4, this is 8, 1 2 3 4, 16, 1 2 3 4, and 1 2 3 4. Well, minus 16, minus 8, 0, 8, and 16. We said that when we are going to convolve x of f with delta of f will be x of f itself. So this will be the first component. Look, this will appear at this point. Okay, this is the first one. When what? When the sampling perform the convolution between the original signal x of f and s of f delta of f. Okay, now then we have what? We are going to perform the convolution between x of f and delta of f minus 8. Again, it will appear at this point. Okay, and with 16 at this point, with minus 8 here. Okay, now of course it's a very simple example, and you can note that what we are going to recover the original signal or easily. Look how, of course, as I have told you before, to recover the signal, to recover the original signal, we are going to use what? We are going to use a low pass filter. Okay, a low pass filter, the low pass filter with cutoff frequency sampling over 2. Okay, in this example, sampling rate is 8 kilohertz. So the cutoff frequency FC, okay, not FS, FC of the low pass filter will be what? 8 over 2, and it will be 4 kilohertz. Look at, if I am going to use a 4 kilohertz, easily we can what? We can recover the original signal without any overlapping. This is about the first example. If you have any question, do you have any question?
Yes, I had, sir.
Yeah, good.
Okay, what's the effect of that? The problem said you should draw from 0 to 20 kilohertz. You didn't talk about it.
Yeah, again, according to the example requirement, okay, they asked us to draw the spectrum up to 20 kilohertz, no more. Okay, so if I'm going to take more sample, more delta f's of the sampling function, 0, 8, 16, the other one will be what? At 24. Okay, at 24. 24 will exceeds the 20 kilohertz. Okay, so again we are limited by the problem requirement, which is 20 kilohertz, no more. Any questions?
Okay,
yeah, of course. Continue.
دكتور
بله.
بس او حالات اخيره او تشكيل اللو باس فلتر سامبلينج بس او تشيا
بله خوب ده او حالات reconstruction يعني we are going to reback the signal to original one. يعني بله خوب ده بس بله خوب ده ام بدش نستري السري تشاوبو او يشين بله خوب ده هذا سيجنالي اصليه هذا سيجنالي اصليه when we are going to recover يعني I'm going to reback the original signal among what هذا تهي چند ويديه هي چند signal هي الفيريجا لكن okay, so we are going to pick up the original signal. So how we are going to pick up the original signal? طبعا بس بريكا لو باس فلتري وكت اوف فريكونسي بولو باس فلتري كاتشاندا sampling frequency تقسيم دو يعني اف سي كت اوف فريكونسي بودالو افيا طبعا افيا 4 كيلو افيا ديجي 4 كيلو درسته؟ يعني cut off frequency بلو باس فلتر ام شاودي تحديد كي سحكا ويدي sampling frequency كاتشندا sampling
ده
frequency
هشتا باي لدو باش دوكي
فرم تقسيم دو نكا اف اكزامبل كاتشندا اف هشتا تقسيم دو دبنا تشار درسته
هذا سباس
عزيزي now the yellow box okay any signal inside the yellow box will be passes the other will be multiplied by what by 0 look at the response of the yellow line okay from -4 to 4 it is 1 outside -4 to 4 it's what is 0 so the whole spectrum will be multiplied by 0 except the region between -4 and 4 will be multiplied by 1 this is the first example is it clear waiting for your response
Yes, doctor, yes.
Yes, it's
Okay.
clear.
Good. Okay, now we became ready to take another example. In this time, the example will be more advanced as compared with the example number 1. So let me take a new page. Okay. Lines and grids. It's okay. Of course, today I'm using an amazing program called 3U Tools. Okay, recommended by Mr. Zana. Thank you, Mr. Zana, again for your help.
You're welcome, sir.
Okay. Example number 2. Okay, example number 2. In this example, we are given an analog signal. Now I'm going to write down the title of this example completely. Okay, we are given x of t, which is an analog signal. In this time, this analog signal is composed of 2 cosine components. Okay, 5 cosine 2 pi 2000 t. Okay, 5 cosine 2 pi 2000 t plus 3 cosine 2 pi 3000 t. Again, this signal, I mean the x of t, is sampled by sampling rate equals to 8000 samples per second. Requirement number 1, x of f. Number 2, xs of f. As you know, x of f, the spectrum for the original signal. Xs of f will be the spectrum for the what? For the sampled signal. Now, before getting into the sketches of these signals, let us discuss some important things. First of all, let's talk about the signal x of t, I mean. Now, look at this signal in this time. We have what? We have 2 components, okay? Component number 1 and component number 2. Now, they are different in what? In frequency, okay? First component in this signal I am talking about, in this signal, we have 2 frequencies, okay? So 2 frequencies we have in this signal, f1 and f2. Of course, f1 belongs to the first component, which is 5 cosine 2 pi 2000 t, and the second component, or the second frequency, belongs to the second component, which is 3 cosine 2 pi 3000 t. At the beginning, I'm going to determine what? To determine the frequencies, I mean f1 and f2. Omega 1 will be 2 pi 2000, okay, and f1 will be 2000 hertz. It's very clear. Omega 2 will be 2 pi 3000, and f2 will be 3000 hertz. Is it clear for you? Is
Yeah,
it
it's
clear?
clear.
Yeah,
It's clear.
good.
Yeah.
So we have what? We have two frequencies in this example. Now, my question is, what will be the maximum frequency?
3,000.
5,000.
Yes, it's very clear that the 3000 is the maximum frequency. Okay, so F max, look, F max equals to what? 3 kilohertz, okay, or 3000 hertz. Now, look at the sampling rate, which is fixed by the problem requirement, is 8 kilohertz. No? Okay, look. According to the problem requirement, the sampling rate is 8 kilohertz. Okay, now, before solving this problem, let us determine the Nyquist rate for this signal. Okay, Nyquist rate equals to what? To F max. Okay, Nyquist rate equals to what? Equals to 2F maximum. So what will be the Nyquist rate for this problem? It will be 2 multiplied by what? 3,000, and it will be 6,000 or 6 kilohertz. Is it clear for you or not?
Yes.
Yes, it's clear.
Good. Now, the sampling rate, which is chosen by the example, is greater than what? The Nyquist rate. Nah?
Yes.
So in this example, again, we don't have what? We don't have overlapping. Well, sampling rate, again, in this example, sampling rate is greater than Nyquist rate. So there is no overlapping. Okay, so there is no overlapping. Is it clear? It's a very important point. It's a very important point to keep in your mind. Okay, it's very important point that the sampling frequency in this problem is selected in a way that's greater than the Nyquist rate. So in this way, we can avoid the overlapping or aliasing. In other words, we can say aliasing. Okay. Now, let us go to the example requirement and try to solve the problem completely. Now, according to this problem, let's go back to the example. 5 cosine 2 pi 2000 t and 3 cosine 2 pi 3000 t. Again, I'm going to apply the Euler identity. So x of t according to the Euler identity will be 5 over 2 multiplied by e to the j, the minus j, 2 pi 2000 t plus e to the j, 2 pi 2000 t plus 3 over 2 multiplied by e to the minus j, 2 pi 3000 t plus e to the j 2 pi 3000 t. Okay, this is about what? About the Euler identity of this signal. Well, 2 pi 2000 t in minus and plus e to the j 2 pi 2000 t plus 3 over 2 e to the j minus j 2 pi 3000 t plus e to the j 2 pi 3000 t. This is about the signal x of t. Now, easily we can draw the spectrum for this signal. This will be the x-axis, or the frequency axis, I mean. F in kilohertz. Okay. This will be the origin, I mean the zero frequency. Now we have two frequencies, 2 kilo and 3 kilo. The component of the 2 kilo will be 2.5 in magnitude. So this is the 2 kilo, and this will be minus 2 kilo. Their amplitudes is 2.5, and we have another component at 3 kilo, which is 1.5. So this will be the 1.5, and this is the 1.5. Of course, this is at, sorry, I did a mistake, simple mistake. I'm going to correct it. This will be, yes, and this is, now the values, this is 2, 3, minus 2, minus 3, and this amplitude will be 1.5. Of course, this is x capital of f. Now, do you have any question about this step? All we have done is applying the Euler identity, then plotting the double-sided spectrum for the signal x. So we have x of f with what? With the frequency axis f in kilohertz. Well, now next step is to plot the spectrum for the function s of f, for the function s of f. Well, now the function s of f, first component at 0, second component at 8 kilohertz, third component at 16, minus 8, minus 16, again, if in kilohertz. F in kilohertz, that's it. Okay, now remaining will be what will be the convolution between these two signals. Of course, after the rest, we are going to take a rest. Then we are going to continue at 3 o'clock with the same ID and the same password. Thank you very much. Yeah, we are going to continue at 3 o'clock, inshallah. Thank you very much.
Welcome, sir.